Ladies and gentlemen, good morning and welcome to Nobel Forum for the announcement of this year's Nobel Prize in Physiology or Medicine. My name is Thomas Perlman and I'm the Secretary General of the Nobel Assembly. I will first read the announcement in Swedish, followed by English. We will then present the background to the prize and open up for questions. Nobelförsamlingen vid Karolinska institutet har idag beslutat att Nobelpriset i fysiologi eller medicin år 2023 ska delas lika mellan Katalin, Karikó och Weissman för deras upptäckter rörande nukleosidbasmodifieringar som möjliggjorde utveckling av effektiva mRNA-vacciner mot covid-19. The Nobel Assembly at Karolinska Institutet has today decided to award the 2023 Nobel Prize in Physiology or Medicine jointly to Katalin, Karikó and Weissman for their discoveries concerning nucleoside base modifications that enabled the development of effective mRNA vaccines against COVID-19. Here are the two laureates. Katalin Karikó was born in 1955 in Szolnok in Hungary. She performed her prize-winning studies at the University of Pennsylvania in Philadelphia in the United States. She is currently a professor at Szeged's University in Hungary and is also an adjunct professor at the University of Pennsylvania. Weissman was born in 1959 in Lexington, Massachusetts in the United States. He performed his prize-winning research together with Katalin Karikó at the University of Pennsylvania, where he is still active as a professor. I will now turn to Professor Richard Sandberg, member of the Nobel Committee, who will now describe the discovery. Please, Richard.
In today's interconnected society, the risk of new pandemics is greater than ever before. When the virus SARS-CoV-2 emerged in late 2019, it rapidly spread across the globe and developed into the devastating COVID-19 pandemic. During the viral infection, the immune system recognizes viral components as foreign, and they induce antiviral immune responses mediated through cells and antibodies. However, this takes time, and meanwhile, the person can develop serious disease. Vaccination strategies have been developed with the purpose of inducing antiviral immune responses that will protect against future infections. For a long time, weakened or inactivated viruses have been used as vaccines. Vaccination programs have been very successful in mitigating many life-threatening diseases, including polio, measles, and yellow fever. With advances in molecular biology, targeted vaccination strategies became feasible. By isolating genetic information from the virus, specific viral proteins could be produced and used as vaccines. Examples are highly effective vaccines against the hepatitis B virus and the human papillomavirus. More recently, harmless viral vectors have been used to deliver viral DNA fragments into human cells to make viral proteins and induce an immune response. Examples are the recently developed Ebola vaccines. The targeted strategies have the advantage of not requiring whole viruses, but still they rely on resource-intensive cell culturing for vaccine production. Researchers have therefore long been attracted to the idea of using messenger RNA, or mRNA, for clinical applications, where the mRNA is used as a template for protein synthesis. The production of mRNA does not require large-scale cell culturing, and future vaccines based on mRNA had the potential to become scalable, fast, and flexible. In fact, major advances were made in the last decades. Researchers showed already 40 years ago that large amounts of mRNA can be produced without cells, for example, using the T7 in vitro transcription system. Moreover, progress was being made in delivering mRNA into cells using different forms of lipid carriers. But there was a major obstacle to development of mRNA-based clinical applications. When in vitro produced mRNA was delivered into cells, it resulted in low protein amounts, and additionally, it triggered an inflammatory cytokine response. This year's Nobel laureates, Katalin, Karikó, and Weissman, started working together at the University of Pennsylvania, bringing with them highly complementary expertise. Karikó had a background in RNA biochemistry and a strong vision of RNA-based therapeutics. Weissman had a background in immunology, working with dendritic cells and their role in immune surveillance and vaccination. It was clear to them that in vitro produced mRNA must somehow differ from the mRNA made in human cells. Delivering in vitro produced mRNA into dendritic cells induced the inflammatory cytokine response, whereas the delivery of human mRNA did not. Using bacterial mRNA, shown on the right side, did also trigger the inflammatory response. Having explored several potential differences in the mRNA, they became interested in nucleoside base modifications. RNA contains 4 bases, often abbreviated as A, U, G, and C. However, these bases can get further chemically modified within our cells. It was becoming appreciated that base modifications were more prevalent in human RNA compared to RNA in bacteria. Could the lack of base modifications in mRNA produced in vitro be the critical factor that leads to inflammatory response? In a series of carefully constructed experiments, Karikó and Weissman used the T7 in vitro system to produce mRNA with various nucleoside base modifications. Each type of produced mRNA separately introduced into dendritic cells while monitoring the TNF-alpha levels, an important inflammatory cytokine. They discovered that mRNA produced with specific base modifications could almost completely abolish TNF-alpha secretion. In particular, modifications to the uridines, highlighted on the right side in orange, made a large difference.